Hi, this is lecture 10 of 11107, lecture 10 part 1. And now we're on to discussing digital pulse modulation schemes. Okay. So this is an extension of the analog pulse modulation scheme, but now instead of uh, just having a discrete in time, a signal that is discrete in time, we also discretize the amplitude levels of your analog signal. And with that, you already have a digital pulse modulation. So just a review of the previous lecture, I introduced to you the different types of analog pulse modulation techniques, namely PAM, PWM, and PPM. And I also introduced the time division multiplexing scheme that is in conjunction with these pulse modulation schemes. When we talk about frequency division multiplexing, we're talking about the use of analog modulation, or continuous wave modulation rather. If we have pulse modulation, we use time division multiplexing for users to be able to transmit in the same channel without interfering with each other. Okay, so why then do we need to shift everything to digital communications? Uh, well, a lot of information to be transmitted are already in digital form in the first place, especially now in an increasingly connected digital based world, computer based world. A lot of data is now represented in bits, in digital format, basically. And the advantage of digital communications is that many signal processing techniques are available to improve even the reliability of the system, and that is not present in analog communication systems. So what are these signal processing techniques? This is your source coding, channel coding, and encryption. Okay, and these are all present in digital communication systems. Your source coding enhances your bandwidth efficiency, how much data can you pack in the bandwidth, and you can transmit that. Channel coding provides error correction, which when you transmit your bits over a channel, some of the bits will be received in error, but the machine has the capability to recover the original message based on its channel coding scheme. And of course, encryption, which secures your data over hackers or over uh, malicious uh, malicious devices that try to gather or harvest data from your digital communication system. Digital communications are also robust against noise impairment, and with the advancements of semiconductors now, we can actually create a communication system with just one microchip, and now even software radios are programmable communication systems. And that's why it's important to know, or it's important that we study digital communications. So if everything is digital now, why did we need to study the analog part of your communication systems? Well, the analysis of a digital communication system is easier if you understand how an analog communication system works. So you'll see as we go along. Okay. Well, in reality, okay, uh, all signals are analog signals. Any physically realizable signal is an analog signal. We treat it as an analog signal. We treat it as such. Right? There are only cases when your analog signal can be thought of as a digital signal. So your analog signal varies smoothly in a continuous fashion. If you're going to sample that, you're basically discretizing the signal. You're discretely getting a sample of it based on the sampling period or the sampling rate. So that is already discrete in time. But that does not qualify for a fully digital signal, because you also need to discretize the amplitude levels. Okay, if both the time and the amplitude is discretized, then you already have a digital signal. Okay? We already did sampling in the previous lecture, and now we only need to quantize or discretize the sampled values to make it digital. Okay, so what is quantization? It's the process of transforming the amplitude of a sample of your sample message, which is continuous, into an amplitude taken from a finite discrete set of signals. Okay? So basically, you're mapping a range of data into a single value. That's it. If your data falls in this area, then we say that it is equal to this S sub 1, which could correspond to a bit notation of 0, 0. And that's how we discretize our signal. The process of quantization converts your analog signal into bit format. Okay? And you'll see here that for a parameter delta, called the quantization step, if delta is smaller, you need more bits to represent that information. And if you have more bits to represent that information, the more you are closer to the original message of your analog signal. Okay. So because of the quantization, because you only represent values at certain points, you represent a range of values at a certain value only, you'll have some form of noise in your resulting signal. If the black line here shown in the screen is your analog signal, if you try to discretize that, if you quantize that, you'll get the blue signal. And if you take the difference between the two, excuse me, if you take the difference between the two, it will result into the one at the middle, the blue curve at the middle here, which is the noise due to quantization. Oh, there you go. It's written here. Okay. So it's the noise due to quantization, and because of that, inherently, if you try to quantize a signal, the output of that results in basically a signal that inherently has noise. Okay? Majority of this of a small quantization intervals resembles a triangular signal, so we can model the quantization error as a triangular random process. Okay, so we can approximate the error to be this to be a pulse of this form. Okay? And to compute for the signal to the quantization noise ratio, we have to compute the power of this quantization noise. So if you get the power of the quantization noise, since it's repeating, right? If you try to square that, it's always has a repeating. It's repeating at a frequency based on the sampling period. The approximate value for the quantization noise power is delta squared over 12. Okay? And to get the value of delta, it's dependent on the range of your inputs. If we say that the input is from negative A max to A max, and we quantize that range uniformly, then the quantization step delta can be computed as this equation. Okay? And this B here represents the number of bits used. Okay? And if we plug that in here, we get this expression for the quantization noise. So now we can solve for the quantization, the signal power is P, then we can define the signal to the quantization noise ratio here to be equal to this value. So inherently, there will be quantization noise. Right? And this ratio, this quantization SQ and R right here, increases, we want that to be very large, increases if the number of bits used are increased right here. Okay? Theoretically, if we have an infinite number of bits, then we can completely represent an analog signal. Okay? So what about signals that have what we call large crest factor? That means it fluctuates from large values to small values. For example, this speech signal right here. A speech signal has a large crest factor. Its peak is much, much greater than its variance. Okay? So the peak of this signal is much, much greater than its variance. Then how do we quantize this? So if we quantize it using a uniform quantizing scheme like this, where the range of values are equal, then the smaller signals will disappear from the speech signal. The one that fluctuates in a small way here, the one that fluctuates here, very small, it will disappear. So it would be better if we use a non-uniform quantization. What is that? Instead of uh, uh, quantizing scheme that has the same that has the same range per symbol, right? We can say that this symbol occupies this range, this symbol occupies this range, this symbol occupies this smaller range, and so on and so forth. That is an example of your non-uniform quantization scheme. And with that, we can represent the smaller signals, right? The smaller signals, if we expand them, and if the larger signals, if we compress them, we're able to fully represent a signal with a large crest factor. The problem is, if you try to design a non-uniform quantizer and try to implement it, it's very expensive, actually. So the solution, a cheap solution to this is companding. You compress the signal if it's very large, and you expand it if it's very small. And there are two commonly used companding techniques for that, the mu law and the A law. The mu law is defined by this equation, okay, and mu here represents a parameter. The m here is the signal, message signal. The A law companding is also used, can be used also, where the A here is used as a parameter and M is your signal. Okay? So what that does is, instead of having a linear response, it has a logarithmic response at which the smaller signals right here are amplified and the larger signals are compressed. So the gain at different values of the input, the gain is different. If you're here, the gain is defined by this slope. Let me just clean it. Excuse me. Okay. The gain of the signal is dependent on its signal level. The gain here will be defined by this slope, which is very large. The gain here will be defined by this slope, which is a little approximately equal to this. And the gain here will be defined by this slope, which is very small. So the larger signals here will be compressed. The smaller signals here will be expanded. That's why we call the process companding. And this is also true using the A law. Right? Now, we move on to representing these digital signals. And these digital signals can be represented using PCM, or pulse code modulation. So a pulse code modulation finishes or completes the analog to digital conversion. Okay? It has 3 steps: sampling, quantization, and encoding. Sampling, basically, you discretize in time. Quantizer, you discretize in amplitude. And encoder represents the signals in bits. Okay? So that's how you get your digital signal. Okay? And this is an example of a pulse code modulation. We sample the signal every t sub s. Okay? So you get this point, you get this point, you have this point, and then this point, and then this point, and so on and so forth. And then you discretize them using your, maybe for this, use a uniform quantizer. So this signal right here will represent 0, this will represent 4, this will represent 5, this will represent 4 again, and so on and so forth. And these signal levels are represented in terms of bits. This 0 here will be represented by 0, 0, 0. 4 here will be represented by 1, 0, 0. 5 is represented by 1, 0, 1. This 4, 1, 0, 0. 3, 0, 1, 1, and so on and so forth. And these are called PCM words. Right? And this is the output of a pulse code modulator. As you can see, your analog signal is now represented as bits. Okay? So because of this, if we represent these analog signals as pulses, your performance can be improved by placing repeaters along the transmission path. Okay? So since, if you recall, as a signal travels through a line, it experiences losses, and the SNR will degrade over distance. If you put a repeater, the repeater will recover the signal from the PCM transmitter. And since this is digital, you'll be able to recover the bits, you'll be able to recover the data, and then you send it again, over and over again, until you reach the destination. You can place a lot of repeaters in the path of the signal, and you'll be able to transmit over longer distances compared to analog signals. Right? So this is an example of your regenerative repeater circuit. There is an amplifier and equalizer so that your distorted PCM wave will boost its signal again, and any channel effects is cancelled out. Then you have a decision device. A decision device will basically do this process again. Your PCM signal could be here instead of here, and then it will say that this signal must be 5 again. Right? Of course, there's a probability that the decision can have an error, right? And this is why we need to use channel coding for the error to be recovered. But that is already for higher advanced communications concepts, right? For higher courses, right? So now, because we have another modulation scheme, of course we'll be interested with its spectral characteristics. So the PCM bandwidth is dependent first on what we call the bit rate. The bit rate is the number of data bits that we can send per second, or bits per second. The bit rate of a PCM signal is given by this, where V is the number of bits representing a binary code word, okay? And Fs is the sampling rate. So it makes sense, right? If we go back here, for every t sub s seconds, you transmit 3 bits. Right? You use 3 bits to represent the data, and you transmit it every t sub s seconds. Right? So for every second for every t sub s, you transmit 3 bits. So that's 3 bits per t sub s seconds, right? And that will be your bit rate. So because this is your bit rate, the bandwidth of the PCM signal should satisfy this condition. Right? The bandwidth should be greater than or equal to the bit rate divided by 2. Right? Why is it the bit rate divided by 2? Since the message signal should follow the Nyquist sampling theorem. Okay? So the problem though is for practical values of V, the PCM bandwidth will be significantly large. Okay? So if we need more bits to transmit per second, then we need to increase the bandwidth. The practical values of V is equal to 10, maybe even 12. Okay? And 12 is already a very powerful microcontroller. But anyway, for practical values of V, your bandwidth actually increases a lot. Okay. However, the major advantage of using this PCM is the ability to multiplex low bitrate signals. In some cases, we don't need a high bitrate, but the channel offers a high bitrate. So maybe we can we can squeeze in a lot of users in that channel, and each of them have a low bitrate. Okay? So this is an expansion of the concept of time division multiplexing, where you use pulse code modulation signals instead of your PAM signals. Okay? And with that, maybe this is your first user, this is your second user, and if you add them all up, this will be the resulting signal. And you extract them based on based on where the user is transmitting. Okay? So there are two approaches. It could be a bit level multiplexing or word level multiplexing. The bit level multiplexing is you alternate the bits per user. The word level multiplexing is you alternate each word per user, as you can see here. So all the bits of all the words, code words of user A is transmitted first before user B. But the concept is still the same. Okay? And that is the end of the part 1 of lecture 10. If you have any questions or do you need any clarifications, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.